Okay, now we have a disk of mass big M, radius big R. It's a uniform disk, mass uniformly distributed over the disk. And we have a force exerted at the rim of the disk, and the force remains tangent to the disk. So that the R vector from the axis, of course the axis of rotation is the center of the disk, and the disk is rotating in a plane perpendicular to the axis. Now all that was kind of implicit. A lot of it wasn't. A lot of it was implicit, not explicitly stated. The R vector then, if the R vector goes from the axis of rotation to the point at which the force acts, we have a perpendicular here. Then, okay, your torque is R cross F. Okay, R is perpendicular to F, and the magnitude of R equals R, so the magnitude of the torque, which I indicate by tau without an arrow over it, equal to the magnitude of the torque, is just then the magnitude of R times the magnitude of F. Again, because these two are perpendicular, the cross product has a magnitude that's just equal to the product of the magnitudes. And that's then big R times big F, because the magnitude of your little r vector is big R. Okay, now, what do we conclude? We conclude that the angular acceleration of the disk is moment of inertia divided by, torque divided by moment of inertia. So that's torque over, well, what's the moment of inertia of a uniform disk? Well, we've developed that, we've derived it, but I repeat it, it's 1/2 big M big R squared. So we have this expression for the acceleration. And then tau is just big R big F divided by 1/2 mr squared. So that's 2F over mr, 2 big F, 2F over big M big R. There's no little f. Okay, well, what happens then? In time delta t, omega changes by how much? Alpha delta t, acceleration times the time intervals you change in angular velocity. So if your initial angular velocity is 0, your final angular velocity is going to be alpha delta t. Follows then that your average angular velocity is 1/2 alpha delta t. And that delta theta then is average angular velocity times delta t. Average angular velocity, again, 1/2 alpha delta t multiplied by delta t gives you 1/2 alpha delta t squared. And that's equal to what? Well, alpha is 2F over mr. So 1/2 of alpha is just F over mr. So that's F over mr times delta t squared. Now I'll mention that if we assume this to be the net force acting on the system, that our development is a little more correct. The reason it wasn't really correct, if we did not assume this is the F net, is that the acceleration is the net torque divided by I, not just plain old any old torque, it's the net torque, sum of all the torques. So if F net is the net force, then tau is the net force, the net torque, and the net continues throughout on all the torques and the forces, and I didn't have that in there before. Now I've put the subscripts in there. They're not written particularly legibly, but all those subscripts on the forces and the torques are nets. So one conclusion we can draw from this, wasn't there before, but the work done then by the net force is net torque dot delta theta. If the force is in the plane of the disk, the tau net and the delta theta are both out of the board, okay, directly out of the board, so they're parallel. So we can replace the dot product of the vectors with just the product, excuse me, of the magnitudes, and then we substitute for tau net the R F net over mr, and something's missing here. Never mind, I thought I saw a mistake, but I didn't. Okay, so that doesn't mean there isn't one. But we do the RF net, which is our net torque, times R delta theta, which we just obtained as F net over mr delta T squared, and we get F net squared over m times delta T squared. Now that is our net work. We can check, and it's always a good idea to check at a point like this to make sure that we have the right dimensions. This is work, so it's got to be in joules. So net force squared over mass times delta T squared should be in joules. And you can check to see that it works out. You get a kilogram squared here, you're dividing by a kilogram, so you've got a kilogram. You got a meter per second squared. Here, squaring it, you got a meter squared per second to the fourth, multiplied by the second squared, you get it from delta T squared. So now you have meter squared per second squared. So this does come out kilogram meter squared per second squared, which is the unit of work. Note that knowing the the moment of inertia, we can set this equal to the kinetic energy if we start from rest, or to the change in kinetic energy, and obtain information about omega. And we can actually come back and confirm, and we can come full circle and reobtain the idea that if omega naught is 0, omega f is alpha delta t. Not going to do that, but just it's kind of important to do these consistency checks. Okay, so now, delta omega, as we know, is alpha delta t. Alpha being net torque divided by moment of inertia, then delta omega is tau net over I times delta t, which is easily arranged to I delta omega equals tau net delta t. So that the change in I omega is equal to tau net delta t. And that's very completely analogous to what? This is analogous to mass. This is analogous to velocity. So this is a lot like mass times velocity, although the units are different and the quantity is actually different. This is not a momentum, and you can check out the units among other things to be sure you understand this is not a momentum. This is what we call an angular momentum, and this is analogous to a net force times delta t, which would be an impulse, but it's not an impulse. Now we call it an angular impulse. So here we have angular impulse and angular momentum by analogy with the change in momentum is net force times delta t, the impulse momentum theorem. So what we have here is a statement that the angular impulse is equal to the change in angular momentum. And this has wide implications, very important theorem. And of course, we could express the same thing in terms of the quantities that we've derived up here. Delta omega being alpha delta t, just as it was over here, is what? Alpha is F net over, is 2F net over mr. So we have 2F net over mr times delta t. And if we multiply both sides of this by 1/2 to get a 1/2 over here, and then work this out so that we just have the RF net here, which is what? Our RF net is our our torque, okay, our net torque. To do that, we would multiply both sides by m to get rid of the m in the denominator, and then by r cubed, by r squared. So we have 1/2 mr squared over here, and we get an r here. So just by multiplying both sides by 1/2 mr squared, we get this, and this again is our torque times our net torque times delta t, our angular impulse, and this is our change in angular momentum, since 1/2 mr is just I. So this is nothing but, let me use a different color here, this is nothing but I delta omega equals net torque times delta t. The same relationship we have over here. In summary, we have this disk with this net force. We get our expressions for the angular acceleration and the moment of inertia, and we find the expression for delta theta. Over to the side, we get the work done in terms of net force and m, and in terms of torque and angular acceleration. And we also get the impulse momentum theorem for this particular object, which matches the impulse momentum theorem that we that generally applies. That is the impulse momentum theorem that applies to any situation. It seemed to apply specifically in this situation.